But for now, I will leave you with Jon Butterworth from UCL, who is going to talk to you about the Large Hadron Collider.
Okay, thank you very much. Thank you. It's nice, really nice to be here, and thank you for coming in out of the sunshine to hear a bit of physics. I'm going to talk you through what's going on in Geneva at CERN, which is an experiment I work on based in UCL, and there are many UK universities and others around the world who collaborate there. I have to confess, happy as I am to be here in Guildford, I have a certain amount of Chicago envy. As you'll hear at the end, there's the biggest particle physics conference in the world every 2 years is going on now, ICHEP in Chicago, where there are some results that have been announced today, which I will finish this talk with. So this is very up to the minute, although the beginning of it is hopefully introductory enough that you can see where we get to by the end. But this is happening now, basically. And the star of the show is this. This is the aerial view you would get as you approach Geneva Airport, which you can sort of see as a beige smudge there, kind of in the middle of the picture at the top of that yellow ring. That's Geneva Airport. On the horizon is Mont Blanc. You'd kind of be approaching it over the Jura Mountains in France. And you can see the Swiss-French border sort of zigzagging along there. And that, the yellow circle there marks, of course, you don't get to see the yellow circle, of course, the farmers would have objected, but they wouldn't let us paint it, but it marks the path of the tunnel of the Large Hadron Collider. It's about, varies in depth at roughly 100 meters underground. It's 27 kilometers around, which, for those of you who are familiar with it, is within a kilometer of the same length of the circle line and the right color, so it's easy to remember. And going around it significantly faster than the trains are the two highest energy beams of particles we've ever managed to get together and control in a laboratory. They're both beams of protons, and they're counter-circulating, one in each direction. And they're brought into a head-on collision at 4 points on the ring, and you can see them marked there on the picture, where it says Atlas, ALICE, LHCb, and CMS. And at each of those points, we have essentially the biggest, fastest, highest bandwidth digital camera we know how to build to record what happens when those protons collide with each other. I'm going to talk today to you about results from the Atlas and the CMS experiments, which are sort of diametrically opposite each other on that ring. Atlas is the one I work on. There are other people in the UK actually work on CMS. And while the other two experiments are interesting, LHCb and ALICE, they're quite specialized experiments, and there's good physics being done there. There's a lot of physics you can do with these beams. But Atlas and CMS are what we call general purpose experiments. So to be honest, when we collide these beams together, we really don't know exactly what's going to happen. That's kind of the point of the experiment. We want to know what happens when these beams collide, and you don't therefore know exactly how to optimize your detector. You don't know what the most important things to measure are actually going to be, so you throw all the technology you can at it and hope it can do everything pretty well. And that's Atlas and CMS. So before I get into the science and technology of that, just to say a bit about the sociology and the politics. This lab, CERN, is a Centre European Recherche Nucléaire, although the official language now is basically English. It was founded about more than 60 years ago in the aftermath of the Second World War to sort of try and rebuild the collaborative open science that had been going on before the Second World War. If you think about it, in the early part of the 20th century, quantum mechanics, relativity, all the nuclear physics, all the advances in physics were coming from Britain and France and Italy and Germany and Denmark and various European countries. By the end of the Second World War, that expertise had been divided and dispersed and had gone, a lot of it to the United States, some of it had gone east, and Europe really was in a mess. And CERN was part of an initiative, it was independent of anything else, it was set up in the middle of Europe in Geneva to basically try and rekindle that basic science. There's no explicitly commercial idea behind it, and also absolutely no military involvement behind it. It was completely supposed to be for peaceful, curiosity-led research. Just about the last thing Winston Churchill did as Prime Minister of the UK was sign the UK joining as a founder member in 1954. And it's been going since. It costs about €2 a year per taxpayer in the European Union. And for us, of course, slightly more pounds than that now. But it's, we've been paying roughly that into it for, it's actually independent of the European Union, of course, but it's, we've been paying roughly that into it for the last few decades. It started smaller, but it's been flat for the last few decades. But it's been a very steady and long-term investment that's very stable because it's done by international treaty. Whereas, for instance, in the US, the budget is set annually and there's always a big fuss about it. And the fact that there's that stability has allowed it to really succeed, and to the extent that now every country that's coloured in here has some formal relationship with CERN, comes there to do science. It is really the one place in the world where you do this really high-energy physics. So, how do we do it? Well, we do it. This is a picture, engineering blowout kind of cartoon of the Atlas detector. You can see it's got a sort of cylindrical structure, and each of these concentric cylinders is designed to tell us something different about the particles that are produced when you collide these protons together. I'll show you a picture of this in a moment, but when you collide them, there's all kinds of stuff produced there, and you really, the name of the game is to work out what particles were produced, what their energy was, and where they were going, basically. So I won't go into it in huge detail, but the central parts, the central cylinder there is a semiconductor detector, which is there's lots of very smart ways of using semiconductors here. This is a fairly stupid way in that you just leave it doped so that with a voltage over it, so it's actually an insulator, but it takes a very small amount of energy to free an electron and create an electron-hole pair, which means you get a current released, and that means you can tell for a very small expenditure of energy, you can tell that a particle went by, and that gives you the track of the charged particle. Then around that, there's a calorimeter, which in Atlas is liquid argon, but the point is it should be something that's very dense, but also allows light and electromagnetic fields to propagate through it, so that when particles stop in it, you get a shock of an electromagnetic field, and that tells you what the energy of the particle was. And then the big wheels on the outside are there to detect muons, which are punched through the calorimeter because they're sort of like electrons, but heavier. So, but that's the only other thing really to say about that. You can see the beam pipe with one beam of protons coming one way, one going the other way. Most of the protons actually miss each other, but some of them will collide right in the center of that cylinder. The others all go around the ring again and have another, several more goes. And the other thing, just in case you haven't spotted it, there are a couple of people standing on the beam line there and down below, so it's pretty huge. It's basically a cathedral for particle physics, and this is one of the kind of iconic images of this that went round when we were building it. This is from 2005, before it was finished. You can see one of the people who was building it in the middle. The kind of pictures it gives us are like this now. So actually UCL was one of the teams that wrote the software for the event display that you're seeing here. I think if we'd have known that it was going to be shown in so many papers and things when we got the first results, we'd have probably hired a graphic designer as well as some programmers, but never mind. It does kind of work, and if you go to Geneva and you've got a couple of hours to kill at the airport, CERN isn't really very far away from the airport. And if you're really into this kind of thing, you can go and see the Atlas control room. There's a visitor center with a glass wall. You can press your nose against the glass and watch physicists at work, and you'll see these events on the screens in the control room, because they actually do give us some diagnostic information about what's going on underground where the collisions are happening. What you can see in this one is three representations of the same collision there. And if you look at the circular one first in the top, your top left of the screen, that's a slice through that cylinder, and you've got to imagine one of the beams coming from the back of the tent, the other coming from behind the screen. They collide in the plane of the screen, and you see all those lines are all particles produced in that collision. The ones that are grayed out and bending, they're lower energy, and they're being bent by a solenoidal field, and that, because they're lower energy, it can bend them. But the yellow lines are hardly bent at all, and that tells you that they're very high momentum, and they punch right through the calorimeter, which tells you that they're muons, in fact, and they register in the muon detectors on the outside. The smaller image there is the other slice. This kind of more rectangular one is the other slice through the cylinder, and you can see the same two muons there. And if you zoom in on the red dot where the beams collide, then what you see is that mess at the bottom of the screen. And each ellipse there is a source of particles, and it tells you that there wasn't just one pair of protons collided, there were many, about 12 actually in this collision, and we get many more these days. The protons don't come one at a time, because most of them miss, so it would take too long to collect the data if we did that. And in fact, they don't come in a continuous stream either. They come in bunches about 2 centimeters long and thinner than a human hair. every 25 nanoseconds, every 25 billionths of a second. And that actually tells that I'm not particularly good at numbers for a physicist, but I know the speed of light is 30 centimeters per nanosecond. And if you think how big the detector is, that tells you that these particles, even if they're traveling at the speed of light, do not have time to exit the detector before the next lot are coming, and then the next lot, and then the next lot. And that's even before they start reading out, we start reading out the detector and getting the signals down the cables, also at the speed of light. We have basically an office block full of computing next to this downstairs. Then there's a tier 0 computing center at CERN, which is another 2 or 3 office blocks full of computers. And then it's farmed out around the world on a computing grid, where there's a tier 1 center in every major collaborating country. The one for the UK is in Harwell in Didcot in Oxfordshire. And then it gets sent to tier 2 centers, which are basically universities, and finally ends up on our laptops and we do physics with it. So when it's running, that's going 24/7 all the time, and there are people on shift all the time doing that. And the data, all the data is shared with everyone on the collaboration. The first paper we wrote based on this was 4 pages long, physical review letters, unless you included the authors, in which case it was more like 20 pages long, because there are 3,000 authors on each of these papers. Sociologically, that's a bit tricky because you worry about people getting the credit for the work they do. On the other hand, if we argued about who went on which paper, it's such a close-knit collaboration that we would never publish anything because we'd spend all our time arguing about the author list. So we essentially give up and put everyone on it. Okay, so why do we want to go to high energies? It's actually, obviously going to high energies is expensive. The reason the ring has to be so big is quite easy to summarize, but it's basically Newton's laws. The problem with these beams is actually not getting them up to high energy. The problem is making them go around in a circle. The centripetal force you need to apply to make these beams turn a corner is huge. It's higher than anything we've ever needed to do. So this tunnel is actually stuffed with the most powerful superconducting magnets we know how to build. And once you've done that, the thing that limits your energy is how sharp is the corner you want to bend the thing round, which mitigates the huge ring. It's big purely for the same reason that corners on a motorway are gentle, so you don't skid off. It would be bad if these beams skidded off. So that's why it's big. It's big because we want to go to high energy, but why do we want to go to high energy? And I've got a massively sophisticated video to show you to illustrate that. What we're essentially doing with this machine is we're looking more closely at, oh dear, let's see if this is going to work. Bear with me a second. It usually does. Okay. Oh, damn it. Okay, maybe it's not going to work. I'll try once more. If it doesn't, then we'll move on. It's not essential. If I can even work out how to move on now. Excuse me. I'm not sure this video is really worth the effort in the end, but that's not good. Okay, stop it. The point of the video is only a ripple tank with water in it, and it would be nice if I can show it you, but I can't by the looks of it. Hopefully I can get back to the rest of the slide. Help? It's not displaying. I don't know why.
Yeah, it's coming back. It's coming back.
Is it? Thank you. Great. Okay, so forget the video. What the video was going to show you was essentially illustrating the fact that you can't see things unless you have a wavelength that's smaller than the thing you're trying to see. So what it was I'm going to do the video with my hands, I think now. What it was a ripple tank where you've got waves traversing it, and you see if you put a blob in the ripple tank, you will see that the blob leaves a shadow, and the waves you can detect with the screen behind the blob. You could tell the blob was there. You could measure the size of it probably and the shape. But if you drop a second blob in, which is smaller than the distance between the peaks and the troughs on the waves, then it becomes invisible. The waves kind of reform around it, and you can't see it on the screen. And that gives you an idea of what's going on in these experiments. What you would see on the video then is that they increase the energy, they ripple it faster, and they shorten the wavelength, increase the frequency, and at some